All right, good morning in Hawaii. It's 5 o'clock Tuesday morning, and we're sitting right above an active flow that's coming down the Pali and flowing into the ocean. There's about 7 of these sites along the coast of the Big Island where the flows from Pu'u'o'o are cascading down the side of the island and entering the sea. It's rather dramatic, particularly in the dark morning hours. We'll get sunrise in another hour or so, but now we can see these beautiful flows of this molten lava coming into the sea. We have to stay upwind because that's not only steam you're looking at, that's hydrochloric acid, so we have to be a little careful. We're being buffeted by very strong winds this morning. This island is a very important site for scientists who are interested in studying volcanoes, and by studying volcanoes, we really can study the uniqueness of our planet. Planet Earth is the only one that can do something like this, and because of it, it creates our oceans and our atmospheres, and as you'll see later in the program, is responsible for life on our planet. I'd like to run over to the geology site, but it's a little far away from us right now, but we'll go over there in a second. But while we go over there, I'd like to introduce to you the geologic team you're going to be meeting in the next few minutes, as well as the other scientists associated with this year's Jason project. Dr. Maddox is kind of a resident expert on the moves of this volcano. He's been walking these fields as a scientist, a park ranger, and an educator. Dr. Sansone has a special interest in the ocean around this island. He's even gone scuba diving in the middle of an eruption. Steve and Frank are going to teach you a lot about volcanoes. To see if these same volcanic processes are at work elsewhere in the solar system, we're going to drop in on Dr. John Spencer up at the NASA Observatory about 45 miles from here. He's heading up that research effort for us. John works mostly in Arizona, but he can look through his telescope on Hawaii using telepresence. Of course, we don't have to look too far to know that one of the things that makes Earth unique is its rich abundance of living things. You may not know it, but without volcanoes, life on Earth might never have developed. We need to examine the way plants and animals have adapted and changed, and the best place to do that is right here with project biologist Ken Kaneshiro. Ken is studying some of the unique species that live only on Hawaii. Closely with a researcher from the National Zoo in Washington, D.C., Cheryl Tarr. Cheryl carries out genetic analyses of the species to create a molecular family tree tracing their ancestors back hundreds of thousands of years. All right, we've shifted cameras. This is an infrared camera you're looking at right now, which we can use in the dark hours to really survey the nature of the lava flows here. You can see the spectacular imagery that we can get with this incredible camera. It not only shows us the surface flows, which are the really bright orange and red, it also shows you the subterranean flows, the bluer features you see there. So we're able with this incredible camera to map the extent of the flows in this area. And so we're surveying. We have a team of geologists that use this during the course of the show, and we can really get a wonderful idea of the total extent of the flows. We're now going to use this camera, and we're going to run off the flow, and we're going to head down towards our base camp, and we'll show you as we traverse towards our base camp that we have lava flows heading right towards it. We've had the base camp, we had to move it a few days after we got here. We set up shop, and all of a sudden the lava started taking us on. It came after us. We had to move the base camp. We've lost over 500 feet of road while we've been here. This is a very active flow, and you can see this one heading right down towards our camp. We're almost there, and you'll see in a second, we'll show you the lights of our facility. We're going to come in and land now, so let's go take her down, and let's pop it down and let me get out. But that's been one of our biggest concerns, is the lava flows getting us while we're doing these broadcasts. So let's go and head down and land, and I'll get out. All right, we're coming in with the helicopter. These night landings are a little dicey, and these lava flows. We've got lights that'll help guide us, but it's still never easy. We're going to send our geologists back up as soon as they buckle up on my straps so they don't fly loose. We're in the Volcanoes National Park, and that's our park ranger, who's our safety officer. He's very critical. I like having him around checking my seatbelts all the time. And later on, we don't send him up into the darkness. All right, we got that baby going. Let's get him going up in the air. I'll fake it. I'll do it. I'm fine. That's pretty exciting. This is our second day of working in the morning, and I don't think I'll ever get used to it. You have no idea how close you are, and so we've got a really good pilot. Unfortunately, we're at sea level, and he looks at his altimeter a lot. Here we are at our base camp. This is just, as I said, a few hundred yards down from the active flow, and we keep looking over our shoulder a lot. This is called the lava flow of Kamoa, which is situated at the base of what's called the East Rift Zone, which is right over there in the darkness. Volcano Kilauea is over that ridge, or pali, and it sits on the flank of the world's largest volcano, Mauna Loa. From Kilauea you can see Mauna Kea, where the NASA observatory is located. All right, we're connected actually by telephone and our JSON network directly to the observatory up at Mauna Kea. And that permits us to tap into their telescopes. It permits us to communicate, particularly we have some Argonauts down here, as you'll see in the background. We have our own telescopes here at base camp, and particularly this hour of the morning, they get a beautiful view. Jupiter's right up over my left shoulder, and they can not only see Jupiter, but they can see the moon of Jupiter, Io, which is the only other place in our solar system where we have volcanism. Over my back, you'll see our biology stations. This is where Dr. Ken Kaneshiro. Ken, good morning. And Ken loves the morning hours because his insects can stay alive. They get cooked during the hot part of the day. But anyway, in addition to that, we also have technology that we are using on the course of the program. We have a Marzikov vehicle system that one of you will be driving later on. And we have a crane system, a lava crane that one of you will be driving. So we've got a really neat technology, a combination of people and equipment. And we'll be going to various sites throughout the morning. Now that we've sort of given you a rough understanding of where we are and the team and the technology, we'd really like to start the program this hour
really from the beginning. And that was when the Hawaiians came here 1,000 to 2,000 years ago. And when they arrived, they quickly discovered that these were not passive islands, that these were very active islands. In fact, there was volcanic activity on Maui back then. And the activity had a lot to do with their religion. And they had a goddess Pele, who was the person who was creating new islands for them, new lands for them. And so in the course of generations, they developed a series of stories that they passed on from generation to generation through the form of Hawaiian storytellers about the goddess Pele. So we're going to begin with a fascinating story about the origin of the Hawaiian Islands through the eyes of the Hawaiian people.
O kaua Pele haka I taiti, I haka kai, me na mako kai. Mahuka mai Pele Hawaii, Mahuka Pele ona onohi. Ina lapa uila, e lapa ina mahinala, eli keumei. Pele Honua Mea was from a land far, far across the ocean called Kahiki. She was born and raised by her parents, Papa Haumea, or Papa Honua Mea as we know her, and Lono Makua, who was her uncle. Lono Makua was the one responsible for teaching her how to make the most lovely fires. It was because of her interest of fire making that got her into trouble back in Kahiki. Namako Kahai, her eldest sister, was the deity of the ocean. Namako Kahai and Pele were constantly arguing about who would take this, arguing about who would take that. Finally, Namako Kahai decided that Pele had to leave Kahiki. Because Pele was a younger sibling, it was Pele who had to leave. And so Pele, downhearted, called all of her siblings together. You'll come with me to our new home over the sea. Nihoa was the first island and Pele and her family came upon. Dig me a pit, she said. Dig me a pit in which we can make our fires, in which we can make our new home. However, the island was unsuitable. They left Nihoa and went on to the island of Lehua. Again, the island was unsuitable. It was not deep enough. There was too much water around. Pele commanded, dig, dig, dig until you find us a new home. However, there was water at the bottom of the pit. And they left the island of Lehua and came upon the island of Ni'ihau. And still, Pele was unsatisfied with the Aina. And so from Ni'ihau, they moved to Kauai. Still, the Aina was not suitable. And from Kauai, they moved to Oahu, and the island was not suitable. And from Oahu, they moved to Molokai. And from Molokai, they moved to Lanai. And from Lanai, they moved to Kaho'olawe until they reached the island of Maui. And it was there in the pit of Haleakala that Pele and her family were able to live and dwell for a little while. Until Namako Kahai caught up with them. And it was there they got into a great battle. A battle which ensued for days. A battle which left Pele, her mortal body, dead. But this did not stop Pele. She again gathered up all her brothers and sisters from the pit and said, we must go. And so Pele and her brothers and sisters went upon Kamohoali'i again, boarded the vessel and came upon Hawaii, the island on which they still dwell. Hawaii, in the pit of Hale Maumau, at Kilauea, on the slopes of Mauna Loa. Here she is today, still building land for us. The cycle of the story begins again.
So as you can see from the story of Pele, that she traveled along the length of the Hawaiian island chain, trying to dig her fire pit and being unsatisfied until finally she reached Maui and then on to Hawaii. That story that you just heard is right on the geology that we now understand. We now know that the Hawaiian Islands sit on the Pacific Plate, and that plate is moving across a great storm in the earth called a hotspot. And as it moves, it burns a hole and creates an island, and then the plate moves again and creates another island. So that sequence that you just heard of in the ancient lore of Hawaiian culture is exactly what we now know to be the truth from a geologic point of view. And to tell you more about the geology of the lava flows here in the Big Island of Hawaii, we're now going to go to our project geologist, Steve Maddox. Steve?
We're walking on the back of a lava flow that started moving maybe a day and a half ago. It's still very hot, and it's starting to ooze along its edges and breaking out and flowing, just small pasty lava flows. Is this your first time walking on an active lava flow?
Yes, it's real cool.
Real cool. Explain what you mean by cool.
Well, it's really hot, but it's really neat. See everything, how it all works, and
it's a lot easier to see the geology at night, isn't it?
Yes, you can see the redness in all the lava, so you can tell where it's actually flowing.
What I'd like to do is walk down to the edge of the flow, and what we can do is teach the students at the pin sites how to recognize an active lava flow.
Okay.
This outbreak is not unusual. We're about 300 feet from a lava tube, and the lava tube can rupture at just about any time if there's enough pressure inside of it. And so what it ends up doing is breaking open and spilling out lava, and this flow has traveled maybe 800 feet in a day and a half, and it still has an active flow front, and that's filling up against the road, and the Park Service is keeping an eye on that. Well, let's come down here by the edge of this hot flow. So right here where we are, we have a flow that's right adjacent to us, and that's maybe 6 to 12 hours old. We're on a flow that's less than a day, or about a day, and right over to our right we have a flow that's about, I think, 3 or 4 weeks old. Derek, how could you tell these apart?
Well, the one that's older, you can see that it's kind of rugged and not as glassy looking, and the newer one you can see more of the lines, and it's just brighter when you reflect the light off of it. Mm-hmm. And of course the new one, you could actually see the lava between the cracks.
Okay, that sounds good. So that's a visual way to tell them apart. What's some other ways we can tell them apart?
You can tell when something's moving almost because you can hear the glass breaking off from expansion of the lava.
Pop and crackle.
Pop and crackle.
So that's your ears. Any other ways?
The heat.
The heat.
Yes.
Okay, let me demonstrate the heat. It's really easy to do. Watch this. So how hot's the surface as a minimum?
Over 100 degrees Celsius.
Over 100 degrees. Usually we don't do that because we don't want to waste our water out here. Can you smell anything while you're down here?
You can smell, almost smells like sulfur, but I'm not sure what sulfur smells like. You can also smell some other things, probably just other chemicals that are in it.
The gases coming out of the lava. Okay, we have a question to us from England.
Okay.
Well, it's not coming in yet. Let's go over to our friend here, Shireen, and give her our tephra traps. Shireen, how you doing this morning?
Pretty good.
Pretty good?
Yeah.
Great. What are you finding in our tephra samples?
Well, there's some of Pele's hair.
Uh-huh.
I see some in here, and it's real thin. There's also some green crystals I see in there.
Oh, those must be the olivine crystals.
Yeah, they're really green.
And the Pele's hair, what's that look like?
It's just thin strands. It looks like human hair. It's real thin.
Mm-hmm. That's pieces of lava that got thrown up in the air by the interaction of the water and the lava, and it just stretches it really, really thin, and then it solidifies while it's flying through the air and then breaks in pieces and falls down onto the bench.
Well, where do the crystals come from?
The crystals are in the lava, and so once they hit the lava, they stop growing. Once they hit the water, they stop growing.
Well, where does the lava flow? We're into the ocean?
Oh, it starts up the hill and comes down this way. If you'd like, we can walk over and get a better view over here.
Okay.
Derek, if you'd like, you can have a look at our tephra samples.
Great.
Bobby, jump back there, Stormy.
Shireen, is this your first time down by the flows?
Yes, it is.
If there's one thing that's constant down here on the south flank of Kilauea volcano, it's that everything changes. For example, this flow is about 2 days old. It wasn't here prior to that. And the youngest rocks were 3 or 4 weeks old. suddenly the tube rips open and everything is flowing. What do you find exciting down here?
Walking here and seeing all the lava in the cracks.
Oh, that's one of my favorite things, to see through the crust, and then down below us there's a glowing rock. It's not lava anymore, it's solidified, it's rock, and it's still so hot it's incandescent. Well, let's go up here and I can give you a good overview of what's going on with the eruption. I have some videotape, if we can look at our videotape. We have a dike system that extends from the summit of Kilauea volcano down into the flank. And these dikes are really conduits that feed the magma from the summit of the volcano down into the flank. And you can see the dike is a very tall feature and maybe 1 meter wide. And so that's how the magma gets from the summit of the volcano down into the flank. So the magma, the liquid rock underneath the surface, gets out to close to the Pu'u'o cone. And there's a lava pond inside the Pu'u'o cone. The active vents are on the flank of the cone, and they formed about 2 years ago, at least the most recent one. So the magma comes up into that vent and then comes downhill in a tube. And the tube's really like an underground conduit, and it might be 10 or 15 feet in diameter. It's only a few feet beneath the surface. But that bridge of rock is strong enough. We can walk over it and there's no problem. You'd probably be able to smell it or maybe tell it's a little bit hotter underneath your feet. So that tube system extends 6 miles down, comes all the way down to the ocean, and it dumps into the ocean at the lava entries, and that's where Bob started us off on the show. Now, sometimes the lava doesn't get all the way to the ocean, and what happens is it comes down and it dumps out on the surface, and that's what we've seen with this flow in the last couple of days. What I'd like the students to see is what the lava looks like when it's flowing along the surface. And what we're going to do is go over to Dr. Frank Sansone. Frank, you there?
Frank. Okay, so we're going to try to get lava temperature here. We're out in a flow pretty close to the site we were just before. And we'll just get a quick idea how hot this is. But so what do we have here?
We have about 400 degrees. It's steadily moving upward.
Can I see it a little bit? Okay. 500.
It's 600 degrees.
Okay, I think this one's going to be plenty hot. This should be about 1,200 degrees Celsius. But as you can see, it's flowing quickly, so we're going to have plenty of hot lava here. Let me put this away. So you guys should take a temperature reading. What we're going to do is put some lava into seawater and see what the chemical changes are in the seawater when we do that. So our starting temperature will be, what is that?
Coming up to about 34.
31.
31.
The air out here is pretty warm. It's about 35 degrees Celsius.
About 27 degrees Celsius.
All right, well, let's go get a sample. So we've got to come down here to the lava flow. And I'll just open up a little toe and get some liquid lava flowing. Ooh, it's hot stuff. And we can drop this in the water. There you go. Ooh, this is gassy stuff here. Do you see all the steam coming out? And the lava is floating in the water, even though obviously the lava rock is a lot heavier than water is. The water comes in, it flashes into steam, and you get a big opening inside. And we're going to let this sit and react for a while. Why don't you take a temperature on this?
All right.
How are we doing there?
Before it was 27. Now it's looking up.
We'll stir it up a little bit.
It's going up to about 45, 44.
Okay, it'll keep going up for a little bit, but let's look at these rocks that we collected yesterday on one of the earlier shows. If you take the rock and open it up, you'll see all these big holes in here. That's where the steam was coming from. Where water comes in and it flashes into steam and shoots out. It's kind of hard to see exactly how what's going on here, but it's with this dim light, but it's very glassy inside from very quick cooling of the lava, so it doesn't get a chance to form nice big crystals. So this is what we see offshore in front of the lava flows, like Bob was showing us on his overflight over there. So, all right, I think maybe we'll go back to Steve. Oh, we have a question. Well, let's see if we can get the question here.
How far in advance do you know when a volcano is going to erupt, and what can you do to prepare for it?
Well, I'm not a geologist, so I'll have to be a little bit vague on this. But certainly, in a place like Kilauea, where we have a lot of studying. The question was, you guys didn't hear, was how do we tell if a volcano is going to erupt? And here in Kilauea, where things are studied so carefully, they have things called harmonic tremors. They can actually use seismometers to feel the lava coming up, or the magma, I should say, going up the magma chamber to the surface. So they can do a pretty good job of forecasting when a big eruption is going to occur. Exactly where it's going to occur, no one really knows. So the best thing to do is just keep on your toes, I think. So, okay. So have you noticed how glassy and shiny this is here on the outside? It's kind of hard on the light here. But if you took a hand lens and looked at this carefully, it looked like a stained glass window. It's green and it's translucent, and you can actually see through it. And if you look down here, we can see some Peles here that we made. We were talking about Peles here before, earlier in the show. Oops. No, it's not a very good example in here. Can we maybe get the camera in a little bit better? You can see Pele's hair, very fine shards. You can see this one stretches, maybe we can see it against your pants. Whoops, it's gone. But anyhow, if you go down to the flows down by the shoreline, they have what they call phreatic eruptions. The seawater goes into the lava tubes where the lava is coming out and explodes real brilliantly. And we saw a good example of that on the shots earlier. So I think maybe we'll go back to Steve and see what he's up to right now. Steve?
Okay, thanks, Frank. We're here with Carl Thornberg. He's a geologist with the U.S. Geological Survey's Hawaiian Volcano Observatory. Carl, thanks for coming down. What do you usually do when you come down to the coastal area of the park?
Well, routinely we're mapping the active lava flows, trying to see where things are hot, and evaluating any potential hazard to personnel or equipment for the park, or in your case, for this broadcast.
How are we doing today?
Well, things are pretty exciting. There's lava to the west of us, lava to the east of us, lava to the north of us, and lava behind us.
Even today.
Between here and the sea cliff. So
oh, wow.
I wouldn't want to camp out here for too long.
Okay, that sounds great. I think you guys have an overflight, or about once a week you go out and do some type of survey of the volcano?
Yeah, that's correct. The routine is to survey the entire eruption site. Beginning at Pu'uo'o, we'll land on the edge of the crater, check out the lava pond, change film in a time-lapse camera that's continually monitoring the level of the lava pond and its activity. Then we'll walk around the rim on Pu'uo'o and collect samples from a tear catcher that catches tears in the plume, and then we'll go down to a skylight at the 2250-foot elevation, throw a cable in, sample lava that's rushing under your feet in a skylight, and then routinely move down the flow to the coastal plain and walk across about a 5-kilometer stretch of active lava that's entering the ocean over this whole coastal plain.
These tears you catch, those are pieces of glass?
That's correct. They're the lava that's in the magma pond, the lava pond at Pu'uo'o, is sloshing around. Tremendous experience to hear and see this. And as it's splashing, it's caught up in the plume, and we have a box that just catches these tears that fall out of the plume and Pele's hairs that are pieces of lava that are caught up in this thing as a result of the lava splashing.
Now, you talked about sampling a skylight. They just watched Frank sample the lava over there. It'd be similar to that, except you're throwing a cable in and pulling it out?
We have a hammerhead on the end of a cable, and we'll toss it into an active skylight.
Sounds challenging.
Right. These are very exciting samples to work on as well.
That sounds good. What's the most exciting thing about working here?
Well, aside from the lava and lava rushing under your feet in a skylight, or standing on the edge and seeing an active lava pond in Pu'uo'o, I'd say one of the exciting things is when the eruption stops, because at that point everybody at the observatory is on their toes, because we don't know where the lava may break out again.
Oh, wow.
It could be down the East Rift where we have populated areas, or back up here at the summit. So we've gotten to the point where we can begin to predict pauses in this eruption. We've had 5 this year in this 13-year-old eruption. And that's when things really do get exciting at the observatory, looking at the seismometers, looking at where things may break out during a pause.
Wow. Thanks, Carl. Thanks for coming down today.
Well, great.
Thank you. Well, let's go over, we have a lava crane, and I'd like to talk about that just a little bit. Go ahead. Guys.
Headlamps, everybody.
Sometimes geologists need to work in very dangerous, very hot environments. And what...
You're in a shadow. Duck.
Move forward.
What happens is that geologists might want to work in a very hot area, like a skylight, and try to take a lava sample or get some temperature data. It's not always easy to do that, and we were fortunate that for the JASON project, the Bechtel Corporation designed an instrument that can be operated through telepresence and go to dangerous places and work. So let's have a look at the lava crane, and then we'll have it a test. We have a probe up front that takes a lava sample. This probe not only takes the sample, but it also gives us some temperature data on how hot the lava is. The other thing, besides the probe, we have an arm. The arm is very long, so it can reach out and take a sample. Attached to the arm, we have a camera. And what the camera does is take a picture so you can see what you're doing. Let's go on around and I'll show you how this thing is all set up. There's 4 legs that hold on to the lava crane. And here's the closest one to me. They've coated it because we're in a very acidic environment. It's wearing this leg down. There's also a winch so that we can adjust it. Up on top, you can see one of the winches that moves the horizontal platform up and down. And this is the horizontal platform, and it moves on these rollers. Let's go back around towards the back end of the crane. There's two instrument packages on the back end. We have a box here, and it's got a lot of switches and motors inside. And what the switches do is control the movement so that we can get a sample. And here's a closer look at the switches. So this is going to move the platform in and out and the arm up and down. We have another instrument that's really the brains of the operation. And it moves the platform through telepresence so that we can take samples from remote areas. We don't have to stand in the hot wind and in the fume. Let's go on around to the front of the lava crane and we can have a test drive. Do I have a student that's ready to work the lava crane today?
Shadows.
Sit down.
Laura? Okay, Laura, what I'd like to do first is have David move the horizontal platform out about 1 second. Great, very good, David. Okay, now Laura, what I'd like you to do is move the crane down for about 2 seconds. Move the arm down 2 seconds. Keep going, keep going. Okay, stop. Very good. Now, probe up. Bring the probe up, please, Laura. Very good. Thank you very much. If we had some active flows that we could sample, we'd be able to get a sample and some temperature data. So this is another successful sampling attempt with the Bechtel lava crane. Laura, if you'd like to, you can bring the probe all the way up, and we can go on to Bob. Is Bob there?
Yes, I am.
Thanks, Laura.
Thank you, Steve. You know, the more we look at volcanism on our Earth, the more we realize the critical role it's played in the, as I said at the beginning of the program, in the creation of our oceans and our atmospheres. And obviously one logical question you want to know then is if volcanism can lead to all these wonderful things on Earth, are they occurring somewhere else in our solar system? So what we've established here at our base camp is an astronomy class that's connected up to the volcanic observatory, or up to the NASA's observatory up on Mauna Kea. But before we go up there and talk to John Spencer, let me introduce 2 of our student Argonauts. You want to introduce yourself?
Hi, I'm Mandela Hunter, and I live here on the Big Island.
I'm Matt Walsh, and I'm from White Plains, New York.
White Plains, New York. Well, do you have any questions about the volcanism on other planets? You've been watching this or looking through the telescopes and studying them?
Yes, I do. Are the volcanic processes on Io the same as here on Earth?
Well, actually, the process of volcanism that creates volcanism here on the Earth is very different. We know that when our Earth was formed billions of years ago through the accretion processes, it collapsed in on itself. Particles were pulled together by the force of gravity, and when they hit one another, they created a lot of frictional energy, a lot of heat energy. And that went on and on and on. It was very violent when Earth was first formed, and it caused the Earth to melt. Also, since the interior. Also, since that period of time, we've had radioactive decay. And radioactive decay has added heat energy to that. So the lava that you see behind us and the volcanic activity here on the Big Island is caused by the heat of origin of the Earth and subsequent decay. In the case of Io, it's very different. Io is a moon of Jupiter, and Jupiter is very large, and they're very close together. And so the gravitational force of Io of Jupiter acts upon Io as it spins, and it sort of distorts it and causes it to have a lot of internal torque. And that energy of distortion leads to melting and the creation of volcanism on that particular moon. So although they both are volcanic in nature, their fundamental origins are different. Do you have any questions?
Yeah, the volcanoes created the atmosphere and the oceans here on Earth, but are there oceans and atmosphere on Io?
No, two reasons why there isn't. First place, Io is very small, and it's unable to hold on to things like we can. When our Earth and the volcanoes degassed in the early origin of our planet, particularly water vapor, for example, there's a lot of water vapor coming out of volcanoes. Our gravitational force of our planet was strong enough that it could hold on to it, and it could cause it to fall back down and form the oceans and the atmosphere. That's not the case on Io. It can't hold on to things because it's not the critical mass or the size of our planet. Is John up and running yet? All right, I guess they're still working to try to hook up John. Any other questions you might have?
What is the star up there that I see, that bright star?
Well, actually, you're looking right up at Jupiter, and it looks like a star, but that's the planet. I think you've been trying to track it down, but we've got cloud cover coming in, and we have a lot of plumes or smoke coming off the volcanic eruption, and it's been obscuring it. But that's Jupiter right up there, and if we could get it in on the telescope, we had a nice image of it a few minutes ago, and you could see right next to it Io. This isn't as powerful as the one up at Mauna Kea, but it's certainly good in this morning. Actually, you can use this when this is your first time here during the day. When the sun comes up in a little while, you can still use it, despite the fact that there's bright sunlight, because it can pick out Jupiter even in the middle of the day. Do you have any other questions?
Yeah, Io is the largest moon of Jupiter?
No, it's not. No, it's not. It just happens to be very close to the planet itself, and we're not sure exactly how much volcanic activity is taking place on Io, but we can identify about 7 major eruptive centers going on there right now. John, why don't you come in and save me? I'm not an astronomer. Can you add a little more information about the different sizes of the moons of Jupiter?
Sure. Hi, Bob. Well, I'm supposed to be observing them right now, but strangely enough, we have snow and ice on the summit of Mauna Kea this morning.
Wow.
So I'm sitting down at 9,000 feet, and which is where we have our dormitories, and hoping it clears up and maybe I can go up later. There are 4 big moons of Jupiter. The largest is Ganymede, and it's the biggest moon in the solar system. The one that we're interested in is Io, which is about the same size as our own moon, but is a much stranger place than our own moon because it has all these active volcanoes on it, which is what we're trying to observe here on Mauna Kea when the weather clears up. Have you talked about why the volcanoes are there?
Yes, we talked briefly while we were getting you up on the line. They asked me the difference of volcanic activity and how that was created. They asked me about the atmosphere. But do you have any other question? Now that we have a real astronomer on the line, I'm real nervous when I get asked these questions live and I don't know them as well as you do, John. Do you have any questions for John?
Yeah, the telescopes on top of Mauna Kea, are they like what's so special about them that they can see so far and so well?
Well, this is really the best place in the world to do astronomy. The air is very thin up there. There's less air to look through. Also, the air is very steady. We have it's hard to take images from the Earth's surface because the air is always moving around and it stirs up the image and makes the image really fuzzy. But from up here, the air is so steady that you can get very sharp images. Not quite as good as the Hubble Space Telescope, but pretty good. And so we can really see details even on a little tiny moon like Io, and at least under good conditions. And maybe you can show the latest picture of Io that we took yesterday. There's a picture that shows Io it just having passed in front of Jupiter, and it's off to the side of Jupiter. And we have, if you've got that image up there, you can see Jupiter, and it's glowing because this is an infrared camera that we're using, which catches the glow of the heat. And there's a lot of heat coming out of Jupiter that you see. But off to the side is a little dot that is Io, and it looks pretty fuzzy in this image. It's not the greatest of images, but we can measure the heat coming off it by measuring the brightness of that image, and that tells us how active the volcanoes are. And we can do that better here than from anywhere else in the world, really. If you can also show the Io eclipse image, which is the one we took 2 days ago, that's an image that shows Io in Jupiter's shadow, and if you have the image up, there's an image of Jupiter looking very large and kind of dark, and those two bright spots, points of light, one of which, the one in the lower right, is Io. And Io is in Jupiter's shadow there. There is no sunlight falling on it, but it's glowing in the dark. And that's because of the volcanoes, this tremendous volcanic activity that's going on there. We're wanting to look at this because the Galileo spacecraft is going to fly within 600 miles of Io in December this year, and it's going to have one chance to get very close to Io, take pictures of all these volcanoes. We want to know where the volcanoes are so that the Galileo spacecraft can point its cameras at them and look at them, and our best way of doing that is to take these pictures from Mauna Kea. That's in that image of Io in Jupiter's shadow, we can see 3 volcanoes that we didn't know were there before we took the picture on Sunday, and that was very exciting to see. And so we've been getting pretty good data, but today, unless the weather improves dramatically, we may not get very much. But we're hoping for better weather soon.
All right, well, thank you, John. We're going to come back down to a little warmer territory. I think we're all, certainly during the heat of the day, it gets very hot here about the 3rd or 4th show, and I think we'll be envying John and his snow up on Mauna Kea. As you've seen in the program thus far, we've talked about the creation of volcanism here on our planet, the role it plays. We've compared it to volcanism on other bodies in our solar system, such as the moon of Io. Now we're going to really start talking a little more about life itself. One of the interesting things about our planet and the role volcanism has played in it by giving us this wonderful temperate climate, giving us an ocean that can act as a tremendous capacitor for heat and moderate our climate, the possibility of life could occur on this planet. We're going to now go and talk to our project biologist, Dr. Ken Kaneshiro, and Ken has been working in the Hawaiian Islands and is aware that not only is the sequential growth of the islands something that the folklore of Hawaii talks about, and certainly the geology, his research and that of his colleagues has shown that the behavior of animals and insects, in particular on this island and the other islands, is directly tied to how old the islands are, and I find that incredible.
That's absolutely correct, Bob. In fact, the geological history and the single file formation of the islands and the chronological sequence of the islands plays a very important part in our interpreting the evolutionary patterns of these flies.
Well, your insects look a little more active this morning when it's nice and cold.
When it's nice and cool, they do fine. But before I get into the story of the Hawaiian Drosophila, let's look at some of the data that some of the pin sites have collected
on
the spiders, and let's see how they've done.
So they've gone out and collected data on the amount of families, I guess. There you can
families of spiders that they collected from the different areas.
So there's quite a spread. I mean, you can see some in Texas, you've got 3, and down in Florida, it looks like you've got 16. What does that mean to have such a divergence in the database?
Well, it looks like what they're getting is that on the continents, at least, there seems to be lots of different families of spiders that they're collecting. But I expect that in Hawaii, there'll be very few families of spiders. And that's part of the story. Hawaii is sitting in the middle of the Pacific Ocean, probably 2,000 miles from the coast of California and 2,000 miles to Japan. It's very difficult for a single individual, a single insect, for example, to have made the long journey across and hit the islands sitting in the middle Pacific. So it's a very rare chance event for an insect or a seed to have landed on the Hawaiian Islands.
So most species, when they get here, do they have a better survival chance because they've gotten here?
Well, yes, it could be. The thing is, when they first got here to Hawaii, there were lots of open niches. The habitat was relatively unoccupied, so there were resources that they could utilize. So they were able to adapt to these different habitats.
Oh, okay.
So those organisms that made it here were able to adapt and speciate. And this family of flies that we've been studying, for example, from a single female that may have arrived several million years ago, we now have perhaps 1,000 species in this one family. And this represents nearly a quarter of the total number of species in the world altogether. So considering the small landmass of Hawaii, the geological newness of the Hawaiian Islands, the Hawaiian fauna and this group of flies that I've been studying represents a tremendous explosion of species. Okay, Veronica, if you'll work this bug cam, and we'll start to show how we can use these various tools and the technology to study the behavior and understand the evolution of biology. So if you'll work that and try to get some of these flies in focus. Jeremy, if you'll get some flies out that we've already collected. Actually, we've gone out into the field to collect these flies using baby banana food that's been inoculated with yeast. Let it ferment overnight, and if we can put it on the tree trunks, we can attract these flies which we've collected here. And we'll work on that in a moment. How are you doing, Veronica? Oh, you've got some flies there. Can you focus that in? That's very nice, very nice. What do you see?
Well, it's eating.
Yeah, it looks like it's feeding, huh? Mm-hmm. Did you see some other behavior? Did they look like they were cleaning?
This one isn't cleaning now.
Yeah, it's just feeding, huh?
Yeah.
Yeah, they do a lot of cleaning with their legs and with on their wings. A lot of that is because the courtship behavior involves visual cues, and they need to keep themselves very clean. Now, we're not going to see very much mating behavior and courtship in this chamber because the temperature is not quite right for them. So why don't we cut away to some pre-taped footage of the courtship, and we can see what happens to these flies. There you go. This is Drosophila claviceti from the island of Maui, and look at how this fly is bringing his abdomen. This is a fly now, and he's bringing his abdomen up and over his head, vibrating his abdomen, displaying his wings, and watch what that male is going to do. He's sticking his mouth parts out, and watch that female. He's actually kissing the male. So here's a male and a female actually kissing, and as part of the courtship display. So the male is using a chemical pheromone. It's like a perfume, which he's dispersing to the female. All this time he's singing. Now here's another species, Drosophila sylvestris, and there's two males here that's going through some fighting behavior, defending a territory to which females are attracted for mating. And this is an actual courtship now. The female is courting is in the front, and the male courting the female from the back. And again, they're going through an acoustical signal and displaying a courtship song at the same time. So here's a very complex behavior that they're displaying, and this is why these flies have been called the birds of paradise of the insect world. Okay, Jeremy, how are you doing here?
Oh, right now I'm just looking at these flies. They're really interesting. On their wings, it looks like they have little pictures.
Well, that's why they're called the picture wings.
Oh.
How do you remember seeing Drosophila melanogaster in your laboratory back at your hometown?
Yeah, back in New York, we did some experiments with them, and these look a lot bigger than them.
Right. Yeah, we probably have the giants of the insect world in Drosophila in Hawaii. Well, why don't you use your aspirator and transfer these flies to the chamber, special chamber here. Okay, great. Now when we put flies into a chamber like this, then we're able to do a lot more behavioral experiments and do mate choice experiments and so on. And also another thing that we've gotten into is I mentioned the courtship songs that these flies sing. By using a very special microphone that we've developed like this and a amplifier, all of which cost about $20. We talk about all the high technology that we're seeing on the show here. But here's a very simple technology, a microphone and an amplifier, which is quite inexpensive. And then a wooden box, just a balsa wood box with a paper bottom and a hole on the side where we can put some flies in. And then by attaching the box to the microphone, just with a rubber band, we can actually then begin to record and hear the songs of these flies.
Does every species of Drosophila use the songs as part of their mating ritual?
At least we've looked at about 3 dozen, maybe 40 species so far out of the 1,000 possible species, and all of them will sing a song. And they're all very different in characteristics. Well, we'll see what these things sound like. Oasis from the island of Oahu. You hear that, Veronica? And we can use this oscilloscope here to look at the waveform, the patterns of the song. And by getting a printout like this, we can actually make a side-by-side comparison and get a fingerprint, so to speak, of the courtship song. So let's listen to a second one, and just to have a comparison here. This is Drosophila melanocephala from the island of Maui. Now this is a very closely related species from the island of Maui, but you can see that the song is quite different, and just by looking at the pattern on the oscilloscope you can make the comparison.
Is there any reason for that?
Well, there's so many species that's found together in the same forest that as part of the courtship and the songs that they display, they have to be quite different, otherwise they might make a mistake as to who to mate with. So they use the song as a recognition between species.
So species often live together in the same area?
Oh yeah, we can get as many as 100 species in the same patch of forest.
Wow.
So, and that's part of the story. We have perhaps 1,000 species on this very small landmass. Obviously you're going to find localities where there could be quite a number of species altogether. And the complex mating behavior that you're seeing, the courtship songs, have all differentiated.
So that leads to the different species?
It's a result of the speciation that we've seen.
Oh.
So that's really basically the story. I mean, there's a lot more to the evolutionary biology of the Hawaiian Drosophila, but these are just some of the tools that we've been using in understanding the evolutionary pattern, the speciation that we've seen in the Hawaiian Drosophila. So I think, any other questions?
I don't know of any.
Okay, all right, so maybe we can cut to Bob.
All right, well, thank you very much, Ken. As you've seen during the course of the program, technology is a very important part of the JASON program. Not only for the scientists, whether they're astronomers or geologists or biologists, technology is critical to their research. Well, it's also, it's also important to us. This, by the way, is one of my little friends here. This is Jimmy Jib. And Jimmy's a very useful little critter. Are you in the union? You're not in the union, okay. Jimmy is really helpful in being able to move around a set when we're stumbling around in the volcano, particularly here at night. He can really go all over. Why don't you go somewhere else and go up there and look across the street and show everyone the technology that's over there. We have across the street from where we are right there we are. You can see our uplink truck, and over there we have one of our student Argonauts who's going to give you sort of a tour behind the scenes. So let's go over to our roving reporter right now.
Hi, this is Angela Casali from Minnesota, and I'm the student Argo, okay? I'm just going to take you behind the scenes, and we're going to take a look at all the technology that makes it possible for you to see this, okay? Let's go. Okay, in here, there's just a bunch of televisions. I'd love to have this job. Watch TV all day. Hi, Art. This is Art, the producer or director, or what are you?
I'm responsible for everything that you really like today. He's responsible for everything that went wrong. Okay. Would that we could just watch television. Yes. Let me tell you where we are, for instance. I say to Barry, my left-hand man, who's the technical director, and I say, let's put a lower third up that describes where we are. And Barry goes, and there's the lower third. I think we're a typical television truck on the side of a volcano. And then I say, take that out. And over here is Jerry. He's my associate director, and he's responsible for coordinating everything that we've planned. And if you pan up here to the monitor wall, you will see that what we're watching is anything but your normal television. It's all the pictures that you can see that show us what is being fed to this truck from every camera and every effect that is on this Jason project. Okay. And then it's going to leave here and it's going to go to the satellite. So what you should do right now is go down and meet Mike Durbin, and he'll tell you about how the satellite works.
Okay, but before I do that, can I push a button? Oh, this one right there. Okay, bye. Okay, well, we go over to Mike. Let's see here. Mike is, they call him the doctor of technology, but you can just call him Mike. Yeah, he's a really smart guy, and he's handsome and everything. See, I gotta brown nose him because he lets me use the phone. So, okay. So this is a pretty big dish. What's it do?
Well, you've been in and seen the video and audio and how they get it all together and they give it to us while we send it out from here and connect it to all the pin sites and people around the country. We also have all the data in here and all of our telephones go through here, which you get a chance to use. And what we're going to do is demonstrate here in a minute what one of the unique things about satellite communications is the time delay. The satellite is 22,300 miles above the equator, so you can see our dish is pretty high here, and we're looking at a very low elevation angle. So from here, it's about 25,000 miles because of the angle. We're not straight underneath. And then it goes down into Dallas, the same distance, and that, at the speed of light, is about a half a second. Even traveling at the speed of light, it takes a long time. So if this works, we're going to talk to Sarah Lee, our audio person in here, and she's going to patch this audio and the audio of a telephone into the circuit. And what the students will hear, and you might hear in your ear, is what happens to satellite delay. So let's see what happens here.
Okay.
Hi, Sarah Lee. Are you there? Let's see. No Sarah Lee. Okay, this isn't going to work because she's a very busy person, so we won't do this.
It's working.
Oh,
it is working.
I am working. Okay, I just can't hear Sarah Lee.
It looks like a Japanese movie.
Can you hear yourself?
I can. It's like echoing.
Can you count when you hear yourself? Try counting. Can you
what?
Hear yourself?
Yeah.
Okay.
Yeah. Echo. Echo.
Here you
go. Go. Just count like
count.
one, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's confusing.
Now you have an idea what the time delay is, so I'll hang this up. What we do to stop that problem so we don't hear it is we have echo cancelers on the station so that people don't really hear that. So.
Okay, well, it sounds like we got to go back to Bob now, so it's great. I just want to say one thing. I want to say hi to everybody in Minnesota at the Bell Museum, and I want to say hi to my buddies everywhere else. Bye.
All right, well, thank you very much. The sun is just about to pop over the horizon, and I'm going to get back in the helicopter and get ready for our next broadcast in daylight as at the dawn here in Hawaii, Tuesday morning, the second day of the Jason Project. We hope you enjoyed your visit to this beautiful island, and we hope you'll join us next year when we go to live underwater. We're going to live in an underwater house in southern Florida off of Florida Keys, and we hope you'll join us there. We'll also have a little miniature nuclear submarine. It should be a very exciting Jason 7. Until then, study hard. We'll see you. Bye-bye.